So we are going to talk about the rigid body today 啦。咁咧，I think you should have a look at the textbook already for some of the parts.
Yeah.
So let's have a look at. I'll just go through it very fast for the first easier part. So we have the definition of angle displacement. We need to measure the angle from a reference level. Then we take the policy to be anti-clockwise naturally. And then, okay. Then for angular velocity, this is a definition that we use for anti-clockwise motion. We take it to be positive z direction. And then this one, like this one, okay. And then there's one formula, this is omega cos r. Now, actually, you need to take care about, we use the cross product here. 你等我一陣，我塊板要轉一轉方向。Wait.等陣。Okay. Let me see. Yeah, okay, fine. Good. So you can see that there's a cross product here. Do you still remember what if with velocity v is equal to omega cos r, what is the magnitude of velocity v? So for cross product, we use the psi theta. Do you remember it for it?
Yeah.
So this is the angle theta. This is angle theta. So actually you can see that why we define the velocity like this one, because the origin of the coordinate system may not be the center of the circle. Just like in this case, okay, the center is at this point, but the origin is at this point. The origin is at this point. So we can't just use Vu to omega times R. Otherwise, but if you use the cross product, that's fine because R sine theta is equal to the radius of the circle. Okay, so you get the same answer. And then after you, if you use the cross product, also you can find the direction of the velocity. That's it. So, shit. Okay, let's go on. This is what we have learned from a long time before, okay? And also you need to know that the equation of motion can be transformed into the equation of motion in the angular motion. Yeah, the rotation motion, equation of motion. Yeah. And then this is what we have learned before, okay, for the acceleration. So let's have a look at the rotational kinetic energy. So my approach in the notes is very in general. So we need to have a look. So first of all, we consider the object that is rotating about an axis. This need not to be the center mass. Okay, it can be not the center mass. So the object can rotate about any point, even the point is outside the object. Okay, even the point is outside the object. Just like the Earth that's rotating around the sun. So and then we need to we know how to find the Ke for each small part. We just use half mv squared. So we need to add them. We divide the rigid body into many small pieces, and then we need to take the sum of the kinetic energy of each piece. So and then that's how we get this form. But every small part have the same angular velocity omega. So when you do the summation here, you can take out the omega square outside the summation sign. But MRI depends on the piece. So we define this one to be the moment of inertia. In some of the textbook, especially for the old textbook, they will call it the rotational inertia. Yeah. So it is a summation mi ri squared and then or summation r squared dm. So then let's have a look at how to find some. Let's go on to this part first. So for every object, you can consider the entire motion to be the sum of the translation motion plus the rotation motion. So if you consider as a translation motion plus the rotation motion, then for the translation motion, you should use the motion of the center mass. For the rotation motion, it is about the center mass. And then every particle have two, you use the relative motion to consider the kinetic energy. So for each small piece, and then the Ke is half mv squared. Then the velocity, VCOM is the velocity of center mass relative to the ground or inertial frame, and then omega cos r is a angular, so it's a velocity relative to the center mass. So when these two velocities add up together, you get the velocity relative to ground. So and then because half mv squared, that means half mv dot v. So you get this form, and then you need to go on to have a look. So if you take the summation, I think there's some, yeah, here is some, one mistake here. Here should be 2, okay? Here should be 2 here. But it doesn't matter, you go now soon, okay? This part, so there is no half here. And then this part, and you need to, can you understand why this one is 0?
Because is it like parallel or something?
Parallel something. Now, you know that for different I, for different pieces of, the VCOM is the same, omega is the same. So we can rewrite this formula as this one here. You can put the summation sign in this part.
Oh yeah.
Then this one, I will call it the taking the center mass as center mass. Why I say so? Because if you remind yourself that how we define a center mass, so we use a summation MRI over summation MI. For summation MI, and then this gives you the position of the center mass from the origin. But for the RI, we take the RI from the center mass.
Yes.
So that means you are finding the position of center mass relative to the center mass. Then this will give you 0. And then the formula will become a very, very neat formula. This is the kinetic energy. So that includes 2 parts. One is a translation Ke, another one is a rotation Ke.
Oh.
This is the kinetic energy in general. That means for any rigid body, okay? For any rigid body, the kinetic energy can be written in this form. The I is a center mass moment of inertia. There's a moment of inertia relative to the center mass. Okay.
Yes.
And let's. So next part we are going to have a look at how we calculate the moment of inertia. Sorry, let me pin the screen. Data. Okay, so for to calculate the moment of inertia, so we need to actually it's quite similar to find a center mass of any irregular object. So let's say this is a ring, and then for a ring, we assume that there's no thickness. So it is rotating about the center. The center distance from the rotation axis to mi equal all the distance from mi to the axis is r. Okay, so you don't need to integrate the mole of inertia of a ring. That will give you the answer half mr squared. And then there's few examples here. If this is a rod, so maybe you can have a look at this part A and part B.
Yes.
I think it's not too difficult to understand the integration in this part, but I just need to remind you that it's better for you to remember these values. But there's some trick in some of the question, because some of the question may assume that the length of the rod to be 2L. So if the length of the rod is 2L, what is the moment of inertia about its center mass?
It's just like 1/3.
Yeah, 1/3. Okay, you just replace the L by 2L, so you get 1/3 ml squared. Okay. So you may also need to remember this value. Okay. But can you see that actually these two values are the same? This one, okay? This one and this one. Can you understand why they are the same?
Yeah, because
You
like
just add
two
another.
sides. Yeah.
And then if you take the mass, this one to be m/2 and this one to be m/2, so you get 1/3 m/2 times L squared times 2. So you get the same answer.
Yeah.
Okay. So then let's go on. So for the thin disk, actually you can consider it as a many different rings. I'm not sure if I've taught you this. The have I teach you this one? No.
No, you did not teach me this.
But have you learned in the training? Yes.
I think he talked about it in tutorial.
Yeah. So I think it's better for you to remember this form. So if you want to derive it, you can have a look at the graph here. So I think you can understand why this area is r d theta.
Yes.
dr times r d theta. So you get r d theta. So what is the difference between this one and the last part? So for r squared dm, okay, the dm you need to substitute the dm to be sigma times dA. Sigma is mass over area. Then, so you get this one, yeah. Any question for this part? Maybe you can have a look. No. No question.
Yeah.
Okay. So if no question, then let's go on. Additional law of moment of inertia. Let's add them up together. So and then if we have a look at the moment of inertia of the shaded ring here, we are not considering to cut the disk into small pieces. We are considering to cutting the disk into small rings. So you can see that for each ring, you know the moment of inertia. That is, actually I can do it like this. Or actually I can write it like this one. For each ring, the mass of each ring is area. So what is the area of this ring?
It's just two pi dr 2 pi r plus dr minus 2 r.
Yeah, okay, 2 pi r dr times sigma. Okay,
Yeah.
and then this one, the moment of inertia is mr squared. Okay, that we have derived before.
Yes.
The moment of inertia of the ring. And then what you need to do is integrate this moment of inertia. Then you get the same form. Actually, you get the same formula. Of course, they will give you the same answer. That is half ml squared. Then let's go on.
Yes.
Cylinder you can consider as a disk, so they will give you the same answer. For sphere, so have you ever do you know this form? This one.
I've seen it before.
Yeah, r squared sine theta dr d theta d phi. First of all, you need to uh, uh, be careful about the how the angle theta and angle phi is defined. As what I told you before, some of the textbook may swap these two angles. But right now, okay, I define the angle theta to be this angle. Eh, Can I write? Yeah. Eh, To be this angle, okay? So, and then you can see actually, my drawing is not too good here. So, and then r times sine theta is this length, and then times d phi is this length. So this one is r sine theta d phi. And this length, you can see this r d theta. Then times dr. That will give you the volume of this small element. So no question, and then let's have a look. Mm, so no question, and then so the distance from the axis to the volume element is not r. Why I say so? Because if you have a look at the formula for the moment of inertia, that should be integrate r squared dm.
Yes.
So if you put the dm here, okay, and then you get the wrong answer because we need to have a look at how we define the r in this formula. The r here is a distance of the element from the rotation axis. So in this case, the rotation axis is this one. This should be r sine theta. Okay. Then what you need to do is do the following integration. Then you can definitely get the answer. You have a look. Okay. But one question here. Let me clear the screen. One question here. How can we get the integral of this one? Eh? This integral. Ha, ha, ha. I think you should have learned about it. You know it? You don't know it?
Uh, yeah. Um,
You know it?
I don't know.
You don't know it? Oh, most likely you will not encounter this integration in the commission, but just let you know about how to do this kind of integration. So let me share the screen of the whiteboard. Okay. So there's two kind of integration that may not in your textbook. I'm not sure if it is in your textbook or not. So let's say this is sine 2m theta. M is an integer, a positive integer. Okay. And then, so how can we do this kind of integration? And another kind is like this one, 2m plus 1. So this is odd number.
Yeah.
So the second one is actually it's easy to do it. So how can we do it? So we just using the substitution. This one can be converted into negative d cosine theta. Do you know it?
Yeah.
Yeah, integration by substitution. And then for this part, you need to convert it into sine squared theta to the power m. So that gives you 1 minus cosine squared theta to power m. And then if you expand this expression, then you will just get a polynomial.
Yeah.
Then you can solve it, okay? Just like the question in that question, okay? So that is the m equal 1, of course, because it's sine to power 3. So cosine squared theta, then d theta. Then I think it's not too difficult to get the answer.
Mm-hmm.
To integrate the cosine theta, cosine squared theta, later on, okay? You can make some trick there, but
Oh, yeah. Isn't it like, isn't it d cosine theta as you wrote it?
yeah, d cosine theta, yeah, okay. I write it wrongly, okay? So this should be negative cosine theta plus cosine to theta to power 3 divided by 3, okay? Pi
Yeah.
at 0. Then you can get fill 4? I forget it. I forget about it. So it should be, so when you substitute pi, cosine pi equal to negative 1, 1 minus 1/3, and then minus negative 1 plus 1/3. Okay. So you get 4 over 3 here. Okay. So let's talk about uh, the the first part. For the first part, actually, it's not easy to do it. We also write as sine squared theta. Then we need to use one identity. Cosine 2 theta equal to 1 minus 2 sine squared theta. Is it? Or you can write it as sine squared theta equal to 1 minus cosine 2 theta divided by 2. Then you can see that you can reduce the order of the trigonometric function by half. Okay. Then what you need to do, you need to expand this polynomial.
Oh.
And then for the odd part, for the odd order, you need to use the method 2. If it is the even order, so you need to use the method 1 again. Okay. Until you can reduce every part into a odd order, odd power, okay, odd power. So this is really not easy to do it. That's it. It's quite similar for the cosine. So this cosine is the symmetric. the same trick. Okay. 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 Okay.
Oh, okay, okay.
So you can capture a screen and then we move on. Okay. How you can see, you can learn a lot of mathematics in this combination. So that's how you get the answer 2 over 5 ml squared. And then we may need to do one. It's not here. I think, is it here? No. So how about a circle shell? I think they have taught you this part. How about if the question is about the circle shell? Do you know how to do it? Or forget how to do it?
Yeah, I forgot how to. I think it's just a.
It's quite similar actually. So
Just same.
for the shell, and then the area of each small element is quite similar to the elements of a sphere. It's just without thickness. So if it is without the thickness, it should be just r square sine theta d theta d phi. Okay, without the r.
Yeah.
Maybe I just share the screen. So I just need to change it a little bit, So I need to change a little bit. So what I need to do is cross out the dr and make this one to be sigma. This is mass over volume, mass over surface area.
Yes.
So this is a sigma. So you don't have this part. You just don't have this part, and then this is r squared. I think the final answer you should get is 2/3 ml squared. I forget about the. Yeah, I think this is 2/3. But can you try to explain in physics why the moment of inertia of a shell is larger than that of a sphere? So you need to look at the definition of moment of inertia. So can you try to explain why? No. Now if you look at this formula, there's a r squared here.
Yeah, is it like the r squared is like constant? Actually, it's not constant.
Yeah, it's not a constant, but the average distance in sphere from the rotation axis is larger than that in the sphere because the mass is concentrated at the shell.
Yes.
So that you can so call the average distance is larger. Therefore, the moment of inertia of the shell is larger.
Oh, okay. Yeah.
Yeah.
Oh, assume the mass is the same.
You have to given the mass is the same,
Yeah.
the distance is larger.
Yeah.
So then let's have a look at two very important theorem. I'm not sure if it's in. I think this will. One is the parallel axis theorem. Now this theorem can help you to calculate the moment of inertia about an axis if the moment of inertia about another axis is given, or you know how to calculate it. So you may ignore the proof here, but you can have a look first. Now this one should be center mass. it must be center mass. Otherwise, this theorem does not hold. So we can have a look. So you can see that this term goes to 0 again. That's what I call taking center mass as center mass. Okay. Then you get this two term. This one is a more of an inertia about the center mass, and this term is a total mass times d squared. Okay, this one. So another theorem is the just like this one. Okay, if you want to find the relation between the moments of the inertia about point A and point B, you need to write out two equations first. Plus ma squared, ib plus ICM plus mb squared. Okay, and then you minus these two, and then you can see the relation. That's it. Yeah. So the another theorem is about the perpendicular axis theorem. This only holds for the lamina, a very thin sheet. So you can see how we define Ix, Iy, and Iz. I think it's not too difficult to understand. Now, for Ix here, y is the perpendicular distance from the axis. Okay. No question. If no question, then let's go on. Okay. So, and then let's go on to the dynamics of the rigid body. So we're talking about the moment. We know that for the moment it's R cos F. But for a rigid body, now when a rigid body rotates about an axis, we have this formula. The next moment equal to the moment of inertia about that axis. Now the axis here need not to be the center mass.
Oh.
Then the angular acceleration. So you can see the proof in the following part. To see if you get any problem for the proof. No question. No.
Yeah, no question.
Mm-hmm. If no question, and then let's go on. Now, actually, if you are talking about a point particle, this one is the if you want to prove this theorem, this equation, we need to starting from a single point particle, and then we go to a system of particles, and then we assume the distance between the particles is a constant. That's how we define how we can get the formula for the rigid body. So, and then for a single point particle, you can see that R cos dp over dt will equal to, you can put the R inside the differentiation. They will give you the same answer. So you can see that the next moment equal to the rate of change of the angular momentum. I think have we ever defined an angular momentum? No. So you know that it is defined as R cos P.
Yeah.
So that's why you can see that in the gravitational motion, And then if the net moment is 0, but the net moment is always 0, because the force passed through the origin or passed through the star, then the angular momentum conserves. But actually for a point particle, the conservation of angular momentum is equivalent to the conservation of momentum as following. Now, the main trick here is that if for a point particle, even you have different forces acting on this point particle, but each forces have the same point of application. That means they all act on the same point because this is a point particle. So for the net moment, it should be R cos the net force. Can you see here? But for the net moment, how you calculate it? You take the summation Ri cos Fi ma.
Yes.
But every forces pass through the same point. That means all the Ri are the same.
Yes.
Then you take the summation Fi, that is the net force. So you can see if for a point particle, if the net moment is 0, then the net force should also be 0. Then that means these two are equivalent to each other.
Yeah.
So for a system of particles, then what you need to do, you add up the mole of inertia together. You just try to go through it. Or actually, you can consider this formula in an easier way. For a system of particles, the net moment can be written as a summation of the moment of inertia of the external force plus the summation of the moment by the external force and summation of the moment by the internal force. Okay. So if you consider only the external force, then they will give you the same form as this one. dl over dt, okay? dl over dt. This one actually equal to summation dli over dt. Okay. Actually, no. It seems no. Actually, no. It should not be like that because the net force should also include the internal force. But actually, you can ignore this part because the moments of all the internal forces will be 0. Let's say these two particles, M1, M2, have the internal forces. Okay, in these two directions, like this one. Then the moment of these two forces is the net moment of these two forces is 0. Okay.
Yes.
So therefore, we get this form. We get this formula. Now we can't simplify more because in general, omega dot Ri is not 0. As what I showed you before. And then for rigid body, so what we need to do, we can simplify the case by assuming that the rotational axis is about It's rotating about a fixed axis, as what we told here. Okay, rotate about an axis. Maybe you can have a look at the proof here. Actually, you can ignore the proof if you don't want to know about it.
Yeah, I understand it.
Okay. So, and then for the angular momentum of a rigid body, we can define it as I omega. But this is only if the object is rotating about a fixed axis. Okay. So let's talk about what does mean by rotate about a fixed axis. So let's give you one example. Okay. So let's say this is the Earth. Earth. This is the Moon. Is the Moon rotating about the Earth about a fixed axis? Or let me say like that. Can you consider the motion of the Moon relative to the Earth be just only rotational motion without translation motion? Now you know the Moon is self-rotating and also rotating about the Earth.
Yes.
Of course, you can consider the Moon is rotating about its center mass, and then there's a translational motion of the center mass. But actually, you can also consider there's no translation motion, but you consider there's only rotation motion of the Moon relative to the Earth. So why I'm talking about that? Why I use the example of Moon and Earth? What there's some special thing about the Moon and Earth? Do you know about it? The motion about the Moon and Earth.
Wait, the motion about the moon around the Earth.
Now, so when you look at the Moon on Earth, so what is special about the Moon? Actually, you can only see the same face.
Oh yeah.
Yeah. So if I put a dot here,
Yes.
dot here, the distance of this dot to the center of the Earth is always a constant. Actually, every point of the Moon always keep the same distance from the center of the Earth.
Mm-hmm.
So we can consider the motion of the Moon be just the rotation motion. There's only rotation motion. Okay, simplify the case more. Okay.
Okay.
This is called a tidal locking. You may be interested why it is like that. Okay, so you may search online YouTube. Okay, so that's called tidal locking. This is related to the tide on Earth, and then because they will dissipate some energy, and then so on and so forth. Okay, you can search it online. It is quite interesting. That's why the moon is always show its own only one face to the Earth. So let's have a look at the next part. Okay, for the rigid body in general. Okay, this is in general. And then I think you may be so not interested in the proof here. Maybe you just take 1 or 2 minutes to have a look at it.
Okay, explain the last part.
Can you highlight which part to me?
Just like this part, I couldn't really see it clearly.
Okay, let me enlarge it first. Oh, so. This part. Let me have a look. What we need to change it. So we need to change it to be in a more in general motion. Because right now here, the velocity, we only consider rotational motion.
Yes.
That's also a translation motion in general. If you still remember, there's the formula, there is R dot R hat plus R fair dot fair hat.
Yes.
It's the same form here.
Oh, okay.
So you may have a look later on. Okay. The last part about the rotational motion is about the work and power. So you have a look at the work and energy, how we define You can just ignore it, okay? So actually, this is the work done by the moment. Work done by the moment. So you need to take the moment and then integrate with the theta angle. And then we can get this form that equal to change in rotation kg. Now, let me write down this one. Then work done by the net force, it should be ds. Okay. That will give you a change in the translation kg, not the rotation kg. Okay. So right now I want to make a summary on what we have learned just now. So now this is much more important. You need to remember everything in this summary. So let me draw a very small table. So actually we have discussed the rotational motion and let me draw some line first. So we have talking about the rigid body that's rotating about an axis, and also the general motion of the rigid body.
Yes.
So we are looking at the formulas. I'm not sure how many rows do we need. So first of all, this one is this is a motion about a fixed axis, rotational motion.
Mhm.
So this is general motion. So we have talked about the form of the moment of inertia. Oh, sorry, the moment. So let's say about SSO. So you take the moment about the SSO, then the next moment should be I, the moment of inertia about the SSO times alpha.
Yes.
And then the angular momentum should be just I times omega. I just ignore this part. And then the energy, the kinetic energy, you can written it as half I omega squared. I think nothing else I need to write down for this part. Yeah, I think nothing else. Yeah. So for the general rigid body motion, the next moment we don't write. Actually we don't use it. The big R is from the center mass. And then the moment or the angular momentum is written like this one. And then the K contains two parts. One is the translation motion and the rotation motion about the center mass. Like this. These are all the equations that you need to remember for the rigid body. Okay.
Mhm.
No question. You can save the screen and then let's try to do some questions together. Yeah.
Okay.
So I need to download another test. So let's have a look at some of the questions in this textbook. This one? Which chapter? I'm not sure which chapter it is. This one. This topic is, you need to have a look at some of the questions, solve the problems. So there's some special skills there. You really need to look at these examples because we don't have so much time to talk about this.
Take a look.
So let's have a look at. Okay, 7.2. This is a typical question about the conservation of angular momentum. You have looked already? So then let's have a look how to solve it. So, and then, but that question is so, so I don't know how to say about it, talk about it. So ignore the transit time. Actually, you can find the transit time easily. So the sand will take off the inner jump at the speed a times omega a. Okay.
Mm-hmm.
Then what is the distance here? How can you find this distance?
I'm guessing you use the
You can see a right angle triangle here.
yes.
So that actually is equal to square root b squared minus a squared divided by the speed.
Oh, it sticks to our drum. Okay.
Yeah, this is b and this is a.
Oh, okay, yeah.
Okay, actually you can find the transit time. Okay, but we ignore this part in this question.
Okay.
The thinly of the sand with the mass ms in the inner surface. So this one has the initial mass mb.
Yes.
And actually that when the sand is leaving the inner jump, there's no forces acting between the jump and then the sand. Therefore, the angular speed of the inner jump will not change. This may be the most trickiest part in this question.
Wait, can you explain why there's no force?
Because actually they have the same speed. They always have the same speed.
Yes.
So when they leave one another, there's no relative velocity. Then there's no force. Just like this is a car.
Yes.
There's a hole here, and then it's full with water. So when the car is moving at constant velocity, actually the water droplet have the same velocity as the car.
Yes.
And there's no forces between the car and the water droplet.
Oh yeah.
So that means that omega A is always a constant. And then there's no external force acting. There's no external force, or you can say there's no external moment acting on this system. Then that means the angular momentum of the system is a constant. So then the initial angular momentum should be, this is a ring, okay? This is a ring. M A squared plus MS A squared times omega A plus MB B squared omega B. This is a total initial angular momentum. And then after time t, the mass of the sand have been decreased by lambda t. Here, they increase the mass by lambda t. And also, if you have looked at, because of the angular momentum, actually, you can write it like this. Still, you can read like this. Okay. So that's how you relate the angular velocity, omega A and omega B. And you know that omega A is a constant. But the final angular momentum, angular velocity of omega B is not a constant. So that's how we do this question. Okay. If no question, then let's go on to 7.4. 7.4. We have a look first.
Wait, can you just use
So what equation we use in this question? Now you need to use one formula, that is the angular momentum. Let's say, okay, I was doing a gazing the instrument package. So that means it's following like this one. Okay.
yes.
Right now at this point there's some velocity B. So I think can you write down the formula for the angle conservation of angular momentum? The conservation of momentum of the point particle. Yeah. This should be just R cos P.
Oh, there's no yeah, okay, yeah, there's no reason. So wait, what is the R relative to?
So where do you take the moment, or where do you take the angular momentum? You should take the angular momentum at this point, at the center of the star.
Oh, okay.
Because the forces pass through this point.
Yes.
If you take the moment of angular momentum at another point, then the moment, then the angular momentum is not conserved.
Wait, so is it just like it's just like V0 cross 5R with
Haha, this is the most tricky part. Because you need to know this R cross P. So there is a psi theta there.
yes.
So the initial one should be 5R times mv naught times psi theta. That equal to R times B, okay? But that's only one equation, but you need to solve two of these. So what other equation will you use?
You use like
From now on, you always need to consider these 7 different different chapters, or you can say topics in mechanics. So first one, equation of motion, force, energy,
Yes.
momentum, moment, and momentum, angle momentum, and also the constraint. So what else you should use in this question?
you use like energy.
Yeah, energy. So you consider conservation of energy. So
Yes.
it's not too difficult to write down. There's half mv naught square plus the GPE, gm alpha 5r.
Yeah.
Half mv square minus gmm of r. That's it.
Yeah.
So then you get the answer. So you can solve using these 2 equations, then you can solve the answer. That's it. So let's have a look at another one. Okay, here in our. So for 7.6, you just have a look. I just show you the answer first.
Oh.
So you have a look at it. Can you draw the 3-bar diagram on the board on the man's body?
Like how like the torque, the net torque is 0.
Yeah, the net torque is 0. But so what forces? Can you draw the forces on the 3-bar diagram? Yeah.
Oh, okay.
Oh, you can use the arrow, okay, instead of drawing.
Yeah. Can you help me erase it?
Yeah,
I
okay.
can.
Why I can't delete it?
I don't know. I can't delete it.
I can't delete also. Yeah, I'm not sure why. I don't know why. Okay. So can you draw the 3-bar diagram? Yeah. Draw the arrows on.
Yeah. So like, I'm gonna draw this way.
No. In the draw function, there's an arrow. This arrow.
Yeah, I know. I don't know where. Oh yeah, never mind. No, like this.
Mhm.
And then this. Sorry, it's like on the feet, and then.
Yeah, you didn't forget to put the centrifugal force on the body, that's it. But is the object in equilibrium by these four forces?
No.
Yeah. So what forces are you missing?
Oh, the frick.
Yeah, the friction in the bottom. So there's
Yeah.
also a friction in the bottom. That should point to the left, okay?
Yeah.
Such that the object is in equilibrium. But normally you will take the moment at the center.
Okay.
So that even you forget the drawing the centrifugal force, that's still fine. Yeah, that's it.
Mhm.
So and then you may encounter some of the question like to find the mode of inertia of the triangle. If like that, and then you need to, it's really very difficult. You need to use a parallel field. You may, I think the tutor may have taught you how to do it, or not. But in one of the question paper in the PhO, they ask you to find a mode of inertia of a hexagon, regular hexagon, of course.
Oh,
Because the question is not like this one. The question is not like a pencil is falling uh, in a slope. This one, hexagon, is falling. So you need to use this one and then to help you to. You need to find the combination of the hexagon so that you can do the question. So that's it, and then let's have a look at 7.13. This is just conceptual question. This is just a conceptual question. So what is conserved? Sorry, in both part A and part B.
so in case A, the angular momentum is conserved, right?
Yes. How about case B?
Case B, is it like in case B, is the mass like decreasing in height?
No. You consider it to have the same. They are in the same horizontal level.
Oh, okay.
Then the answer should be
I think case B, the angular momentum is also conserved.
no. But why the angular momentum is not conserved? Because the tension is not passing through the center.
Well, what do you mean center? Like,
So the tension here does not pass through the center of the center.
oh yeah. So
So that's net moment. Now you can only take the moment about a fixed point.
mhm.
You can't say that, oh, the points that I take the moment is the contact point, or is the, how can I say, is the end point, the end point of the contacting wire. No, you can't do it like that. This point is rotating, okay? This point is rotating. So actually what is conserved in this case is the energy. Is it a surprise for you?
uh
Is it a surprise? energy is conserved in this case. Because if you take if you have a look, the velocity of the object is always perpendicular to the tension.
Oh, so there's no work done. Yeah.
There's no work done on the object by tension. Therefore, the energy is conserved. Therefore, the answer should so this case energy is conserved. Okay.
Okay. Yeah.
So then let's have a look at 7.14. This is really a typical question in moment of inertia.
Okay.
So how about part A? So this is quite easy. What should the answer for part A?
Is it just like mg over 2?
Yeah, MGL would do. So just remind yourself that you need to take the weight is the center.
Yeah.
MGL over 2. So what is the angular momentum? Which equation will you use?
You just use oh, you mean momentum? It's just I omega, right? If you're talking about angular momentum.
Momentum. But this is not talking about the angular acceleration.
Oh, sorry. So it's just like torque equals to.
Yeah, torque is equal to the angular mole of inertia times the angular acceleration.
Yeah.
This one is mg L over 2. Then how about the moments of inertia about point B? Now, because you're taking the moments, everything about point B.
Yes. So it's just what is it again? Sure, I forgot.
So what is the moment of inertia about point B?
Is it just like is it half mv ml square or something? Actually, one third ml square, right?
Yeah, no, it's 1/3 ml squared. ml squared.
Yeah.
So the alpha you get here, it should be 3g over 2l.
Okay.
So for part C,
Wait, the vertical acceleration of the center of mass at the instant is just.
this is about the center mass vertical acceleration, this one. That
Yeah.
means acceleration at this point. So what equation you can use is the general form of the acceleration.
Oh, yeah. Oh, okay. Yeah.
Then you can find the acceleration. Actually, it's not too difficult.
But what is
R is the this is a position vector from the origin to that position, to that point.
Okay, wait, so like you set the origin as B, right? Or
Yeah.
okay.
Because it's natural, it's very natural to set the origin to point B, because you can see that the motion of the center mass is above point B.
Mhm. Wait, then how do you find out?
How do we find
theta dot and like.
Theta dot is 0 because it's initial arrest.
Oh, okay, yeah.
So actually, you can get this 0, 0, 0. So the final answer should be L over 2 times 3GO2L.
Oh, yeah. I see.
And then for part D,
But what's fine by inspection?
you, you just ignore that these two words by inspection. Ignore these two words. But definitely you need to use the answer in part C to find the force. Just a hint for you, you need to find the force, you always need to draw the free body diagram.
Okay. I'm not sure like where you set the pivot. Like, can you set it as a? Can you set it like
Point A?
Yeah, can you set up?
Yes, but it will be much more difficult because
Oh,
you know that the object is momentarily is rotating about point B.
yes.
So it's natural to set the origin to be point B.
Yeah, but like there's a force on B, right? But like if you
Yeah,
origin, then like technically there's like no torque. Like
yeah, no talk by this force.
yeah. So how can you find the force?
So to find the force, we can use FUMA. Yeah, that's actually it's not difficult. Okay, if you haven't learned this topic, okay, you probably can find it.
Oh, okay.
Just like that. Okay. So most people think that the wishboard is the most difficult topic in mechanics because you really need to use all the equations that you've learned
Yeah.
to do the questions. Yeah. So therefore, the answer should be this one.
Okay.
Okay, you can save the screen and then.
Yeah.
Okay. Oh, do you save it or?
I saved it. Yeah.
Okay. Sorry. I forgot to save it also. So if you haven't saved it, I can send you.
Yeah.
This 7.20, you can do it after the lesson. Okay. This is a really quite simple question. Really simple question. And then so let's have a look at this one today. So 7.37. The plank and ball, a plank of length 2L. So that means after the collision, the ball has a velocity VF, and
Yes.
this has a velocity V.
Yes.
And then definitely we can write down the concentration of momentum. Okay, so why I say half English? I want to write half English quick. So what else you can use? You have two unknowns here. Is it?
Yes.
No, actually you need to use three unknowns. There is also an angular velocity of the Planck.
You're fine.
Yeah. So what other formula we use? Of course, you need to use the energy, okay? Because
Yeah.
I show you the energy is concept. So initial energy is so easy.
Yes.
Then the final energy of the ball, so easy. But you know that the Planck is moving in general motion. So there's two parts in the kinetic energy. One is a translational KE.
Angular.
Yeah, another is angular momentum. But the angular rotation KE.
Yeah.
So another formula you need to use is the angular momentum.
Oh, okay.
Yeah.
So
So I'll take the angular momentum at 2 points. So let's say if I take the angular momentum at this point and also at this point. Okay.
mhm.
So let's say if I take the point at point A, then the initial angular momentum of the ball is 0 because R cos P. Then R cos B is 0 because R pass through the point A. Okay. And then after the collision, and then the angular momentum of the ball is also 0 because it passed through the point A. That means the initial is 0. But the Planck has angular momentum. But of course, the sum of the angular momentum should be 0. Now, clockwise, take it to be positive. Sorry, take any clockwise be positive and take clockwise be negative. For I omega, it is and clockwise, okay? Take it negative. So this should be negative I omega. And then the R cos P part, okay? R is from point A to here, okay? So this is anti-clockwise, R cos P. So you need to take it to be positive. So R times P, R is L, okay? The length L. P is MV, okay? Then you can use these three equations to solve the three unknowns.
Wait, sorry, can you I didn't catch that. Can you explain why it's negative?
Because it's clockwise.
Oh, okay, yeah.
Clockwise should be take negative, and then anti-clockwise should take negative, positive.
Yeah. Okay.
Okay. So you can not taking the angular momentum at point A, but as obviously if you take the point angular momentum at point A, it's much easier for you to do it.
Yeah.
So if you take the angular momentum at point B, it's still fine. The initial there's initial angular momentum of the ball. This is a clockwise moment, clockwise angular momentum. So that should be negative L mv naught. Okay. Yeah. So let me write down the formula. That's it. Any question here?
Oh no. Oh, I was wondering, like, can you
Mm.
can you express like omega in terms of V?
No, actually they are not quite related together.
Oh, okay.
You need to solve it, and then you know the answer.
Mm. Yeah, I have no questions.
Okay. So we will talk about the remaining part next time.
Yeah.
Next session. And then we will go on to talk about much more question on rigid body. This is the most difficult topic in mechanics.
Okay.
Yep. Okay.
Yeah.
And then so see you next week.
Okay.
Bye bye.